Hi, it's time for another math easy solution. Today we're going to discuss a pretty interesting topic, and that's on conic sections, part of my new series. And now we'll look at parabolas and go over the definition, or the formal definition of a parabola, and just briefly talk about conic sections. So in this section we give geometric definitions of parabolas, ellipses, and hyperbolas. I'll go over these ones in later videos, and then derive their standard equations. They are called conic sections or conics because they result from intersecting a cone with a plane as shown below. If you slice this kind of cone where you have a mirror image of two cones like that, if you slice with a plane on one of them that connects both sides of this top one here, then what we get is an ellipse. If you have it flat, it becomes a circle. And a parabola is you slice this one at an angle so that it doesn't enclose itself like a circle over there. So you get an ellipse. Basically, these just go on and on. And then to get a hyperbola, that's you slice vertically. So parabola slant, an ellipse goes through both or the full cone like that. Now hyperbola is vertically, that slices through both of the top and bottom, so that you get essentially two parabolas. So you can think of it as like that. So you get two parabolas, and there's one. Basically the hyperbola goes up and down when you slice it like that. So in this section we'll look at parabolas and go over the formal definition. So a parabola is a set of points in a plane that are equidistant, i.e. same distance from a fixed point F called the focus, and a fixed line called the directrix. I believe that's how you pronounce it. It's a quick reference, equidistance, here's from mathopenrev.com. So a point P is equidistance from others if it is the same distance from them. Basically in this case we have P is equidistance to Q and R. So for example, P right here is basically the same distance to Q and R. So wherever you move this as a cool animation, you can move this around, and basically these move around so that they're always the same distance from the point P. So let's look at the definition. I'll illustrate it. So parabola, set of points in a plane that are equidistant, i.e. same distance from a fixed point. If you look at it through this plane, it would be somewhere like this could be the point F, and then the fixed line could be this somewhere across here, etc. And we'll get to that in a bit. So it's going to be a set of points equidistant from a point F and a line called the directrix. So let's draw this out. Let's draw the point F here, and all this is, again, that's point F. This is the focus. And now what I'll do is I'm going to draw a dashed line across here. So it's the distance across here. Now we have the directrix here, and I'll call this the directrix. So now if we have directrix there and a point F, these are both fixed, a fixed line and a fixed point. Now we want to find points that are equidistant. Basically parabola is all of these set of points equidistant from those two fixed point and line. So for example, here, if we were to look at the distance from here to a point, let's say if we keep going up, so if it's from this one right here, it has to be right angle because that's the closest distance is just vertically down to it. So if we go up, if we keep going up, it needs to get to a point where it's going to be equidistant to that one. So it's going to be somewhere here in this case. Actually, I think it might be a bit higher. Let's draw this a bit higher, maybe here, like that. So that looks like it's a bit closer. So this is going to be the same distance across there. Now if we have another point, let's say from here we're looking at the distance, so it's going to be going up and up until it's equidistant from there. So it should be, this should be something like this. So this is going to be the same distance across. And likewise, if it was right across here, that would just be in the middle here. That's just be in the absolute middle there. So on this side, we're gonna get a shape that looks something like, like this. I just erased that and make it in black here. So it looks something like that. That's our parabola. Well, that's one half of it. Yeah, and likewise, if we have it on the left side, it's going to be pretty much exact same thing. Let's pick another point here. I'm going to go up like this one. This is going to go, yeah, this is pretty much it there. Just have to make it 3 of these. And yeah, so you could do this infinite amount of times. It's always going to be, it's going to result in a shape that looks like this, where this is the parabola. So that is definition of a parabola. Yeah, and now notice that the point halfway between the focus and the directrix lie on the parabola. It is called the vertex, and that's this one right here. Yeah, and here I quickly just fix it up so it looks like more equal here. Let's draw a line like that, equal distance across there. So that is the vertex. I'll draw this as that's the vertex like that. And also the line through the focus perpendicular to the directrix is called the axis of the parabola. That's just this line going through the focus perpendicular to the directrix. That's just the axis like that. So yeah, now that we've drawn this definition out, I just want to go over a brief note. In the 16th century, Galilei showed that the path of a projectile that is shot in the air at an angle to the ground is a parabola. So for example, if you have a cannon, I'm just going to draw one like this. Let's say this is holding the cannon, and then we have something like this, etc. And then let's say you fire it off, you blast it, and then basically, yeah, whatever it shoots out is going to be in a parabola. Let's say it's a cannon, etc. And then you have a parabola shape of its travel path. So yeah, that's a very cool discovery by Galileo. And yeah, now since then, parabolic shapes have been used in designing automobile headlights, reflecting telescopes, and suspension bridges, and yeah, much more. I may go over an example in a later video that goes over the reflection property of parabolas and makes them so useful. So hashtag stay tuned. Because yeah, I didn't realize that even in automobile headlights they use parabolas. That's very cool. So yeah, stay tuned for that video. Alright, so now let's get back to the parabola. So we obtain a particularly simple equation for a parabola if we place its vertex at the origin and its directrix parallel to the x-axis. Yeah, as shown in the figure below, which I will just draw right now. So let's say we have our typical xy axis like this. That's x, this is y. And now let's place that vertex right at the origin. So we place it right at the origin O, and now we have a parabola like that. And now its directrix is parallel to the x-axis. So if we have it like that, and then when we have the directrix, I'm going to draw this in light shading over there, and this is just our directrix there. Yeah, so in this case we're going to have a focal point exactly the same distance from here to here somewhere, so it's going to be somewhere like that, and this is our point F. Yeah, so if the focus is the point 0 and P, then the directrix has an equation y equals negative P. So at this point, let's say the distance from here to there, that's just P. Yeah, so this full distance is P. So that means at this point we're going to have 0 for x and then P for y, and that's our point F for focus. Now this is just a horizontal line right here. So that means here we just have y equals negative P, because this full distance is just P, or negative P across there. Yeah, it's a distance of P. Yeah, I'm just going to erase this and erase this, just so I could say this is the distance P, so it doesn't look like it's a point there, and this one is negative P across there. Yeah, like that. Actually, I'm just going to remove this. Yeah, it still looks like it's a point there. Draw this for equidistance. So now that we have that, what we can find out is if the point PXY is any point on the parabola, then the distance from P to the focus is, and I'll get to that in a bit. So let's say we have a point P across here. So this is point P and its coordinates are x, y, like that. Yeah, if its coordinates are x, y, and now let's say we have a line across from here to here, and then also we can extend this past from there to there. So now we have a triangle like this. Now distance from F to P or P to F, I'm going to call this PF, an absolute value like that. Now we know this distance is just x. This is just x across, because that is if we just extend this pass down all the way across here. Another, again, right angle. This is just distance, or at this point is x, like that. So that's coordinates x, y. Yeah, so now I'm going to move this just to make it easier. Move it right over there. Actually, move it back there just a bit higher. Just so that we can get this point right here. We know that from this one all the way to across here, that's just going to be, well, P. And now this distance is just going to be y minus P. So now we have a right angle triangle, and we could just use Pythagorean Theorem to solve for the distance PF over there. So let's write minus y minus P. That's because its full length is, well, we know the coordinate, that's just y. Yeah, so what we have is that triangle. So recall the Pythagorean Theorem, theorem like that, where we have here, now we're going to have the hypotenuse squared equals to the addition of the x and then the y minus P squared. So we have PF, the distance squared, equals to x squared plus y minus P squared. And then when we square both sides, we get, well, PF, the distance, equals to plus or minus square root x squared plus y minus P squared. Except we're just going to look at the plus because we're looking at distance. So it's going to be the absolute value, hence this absolute value sign there. Yeah, and now the next step is, well, the distance from the point P to the directrix is going to be the absolute value of y plus P. That's because, well, distance from here all the way to the directrix, if we just extend this, move this x there, if we just keep extending it, we know that, well, this distance across like that. Yeah, just fix things up a bit. So just write P distance across there. So then the full distance from here to here, that is just y, or absolute value of y plus P, because in case we ever have a negative P. So the above figure illustrates the case where P is greater than 0. Now, the defining property of a parabola is that these distances, distance from the directrix and distance from the focus, are equal, i.e. equidistant. Yes, so what we have is the absolute value of, or the distance from P to F equals the distance from P to the directrix. Let's write it as this. Yeah, so thus what we have is that's the distance there, square root x squared plus y minus P squared equals to the distance right here. Yeah, this one right here, y plus P, so absolute value of y plus P, like that. Yeah, so this is, again, that's definition of the parabola as explained above. So now we have it in equation form. Yeah, we can just get an equivalent equation by squaring and simplifying. So when we square that, what we get is, well, let's just square this. Y minus P, then, well, yeah, this one like that. Let's write it down and then square it. So squared. So what we have is, well, the square roots cancel, so we're just going to be left with x squared plus y minus P squared. And now this equals to, on this side, that's just, well, the y plus P squared. So we could remove the absolute value sign, and that is because, just make a side note like here, i.e. any number, when you square it, this is always going to be greater than or equal to 0. Because if it's negative, two negatives become a positive. Yeah, so then we could just remove that absolute value sign like that. Yeah, just fix up the bubble and the arrows. So now what we could do is expand this using the FOIL method. So now what we have is x squared equals 2, and now if we multiply, just expand this out, so y times y is y squared. That's not an equal sign, it's a plus. So y times y is y squared. Y times negative y is y times negative p. I mean negative py. And now we do the opposite. Negative p times y is again negative py. We'll add 2. That's the same. Just add them up. And now what we have, negative p times negative p is plus p squared. And now on this side what we get is y times y is y squared. Y times p is, again, py. P times y is py, so we have a 2. And then plus p times p squared. Just did the FOIL method in my head there. So now that we have this, now what we could do is subtract or cancel the like terms. So plus p squared, we could just cancel with this plus p squared. Y squared, and there's a y squared we can cancel. And now what we're left with, this is negative, that's a plus, so those actually combine. So I'm going to move this over to this side, and what we're left with is this x squared. So we're left with x squared equals 2, so negative 2 becomes a positive on this side, becomes 4py, and there's our standard equation for a parabola. Yeah, so thus what we have is an equation of the parabola with focus 0 and p, and directrix y equals negative p is x squared equals 4py, like that. So that is basically a definition of the parabola in standard equation form, and that's the formula of it. I mean, yeah, that's the formula from the definition as explained above, the equidistance from the focus and directrix. So now, interesting, if we write a equals 1 over 4p, then the standard equation of a parabola above becomes the more common. So if we do that, what we'll do is, well, let's just write this, x squared equals 4py. So I'm going to just divide by 4p, divide by 4p, we get y equals to x squared over 4p, and if we let that equals to a, this just equals to ax squared, which is the more common parabola. So we have our y equals ax squared, the common parabola formula. Again, because a and p are constants, so just write it like that. So because 1 over 4p is still a constant. Yeah, now, the parabola, it opens upwards if p is greater than 0, and downwards if p is less than 0. And to illustrate this, I'll draw these out. So for a, let's say the a graph is x squared equals to, again, 4py. We have p is greater than 0. That's exactly as the one above. So what we end up having is a shape like this, where this point here is 0p. Yeah, 0p like that. Now we have our directrix going to be somewhere here, like that. So this is our y equals negative p. So if it's positive, that's going to be at the bottom. This is going to be positive like that. And our parabola goes up like that. And again, this is our y-x curve. And now for the other section, if p is less than 0, again, we have x squared equals 4py. And now if we have p is less than 0, what this means is 0p is going to be, well, that's going to be negative. It's going to be on the bottom. So if we draw this out, y and like that, x. So we're going to have the point here is at our 0p, where p is negative, and then negative p is going to be, well, positive. So this is y equals negative p, which is negative times negative becomes positive, and then it just goes downwards like that. And now also note the graph is symmetric with respect to the y-axis because the equation is unchanged when x is replaced by negative x, i.e. if we have x, or I'll write 4py, this equals to x squared, which also equals to, well, negative x squared. And that just equals to, well, again, whatever negative becomes positive, so x squared like that. So as you can see, it's a mirror image about the y-axis like that. So mirror on both of these is a reflection of the y-axis. And now if we interchange x and y, what we obtain is, well, we just switch these around. So that just becomes y squared equals to 4px like that. And this is just the inverse of, yeah, this is the inverse function. And then what we'll obtain is just parabolas that are horizontal, opening up as opposed to the vertical up and down. We get left, right. So again, which is just an equation of parabola now with focus because we're switching x and y. So now we have x is p, y is 0, and at directrix the formula now is x equals negative p. And interchanging x and y amounts to reflecting about the diagonal line y equals p. See my earlier videos on inverse functions just to learn more about that and see what that is. So the parabola opens to the right if p is greater than 0, and to the left if p is less than 0. And we can draw this out. I'll write this as figure C. So if we have y squared, or y squared equals to 4px like that, and let's say p is greater than 0. So what we end up having is a yx like that. Let's draw this a bit smaller. So we've switched everything, so the focus is now p and 0. If p is greater than 0, it's going to be somewhere here. That's our p0. So then x equals negative p is going to be on this side here, like this. I'll draw it like that. This is our x equals, it's a vertical line, so x equals negative p, like that. So then this opens up this way. There's our parabola. Now for the last one, D, this is y squared equals 4px. Now this is y is, p, so I could erase this. So that's p is greater than 0, and p is, this one is less than 0. So this means that the point, if this is y, this is x. So if we have the point p is less than 0, the point p0 is going to be on the negative side right here. That's our p0. And now what we'll have it at the x is negative, p will be on the positive side. It'll be like that. This is just x equals negative p. So then this opens up like that onto the left side. So yeah, it just opens up on the left side like that. And in both cases, the graph is symmetric with respect to the x-axis now, which is the axis of the parabola. So extend this past, or I'll just write it here. This is just a mirror image like that on about the x-axis. So yeah, that's pretty much it for the definition of a parabola. And it's again, it's a part of the conics section series, so stay tuned for my other videos. It's gonna be quite interesting. Anyways, that's all for today. Hopefully you learned and followed through, and like always, you can download these links, these notes in the link in the video description below. Also, just want to get back to here. So as you can see, this is the section about this parabola. This parabola is a section about this cone, and then there's our directrix line there, and it keeps going on. There's the focus somewhere across in there. And yeah, that's all for today. Again, download my notes in the video link in the description below, as well as on Steam in article format. I'll upload those shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another math easy solution.